So now we're going to start delving into divisibility proofs. And the most fundamental thing to understand about divisibility proofs is that this statement or this question is in fact true. It is true that for any integers a and n, a always divides a multiplied by n. We're basically trying to prove the definition of divisibility, or trying to prove that the right-hand side, when it's a multiple of what's on the left-hand side, is in fact divisible by what's on the left-hand side. So how do we start this proof? Well, first we have to understand what divisibility means. What does this line mean? What this line means is whatever on Earth is on the right-hand side has to be a multiple of what's on the left-hand side. So if you have something like 2 and 4, or 5 and 25, or 6 and 60, right? You're basically asking, what's on the right, can it be a multiple of what's on the left? So in this case, can 4 be a multiple of 2, or can 4 be 2 times something? Here, can 25 be a multiple of 5, or can 25 be 5 times something? Here, can 60 be a multiple of 6, or can 60 be written as 6 times something? Now the something that these have to be multiplied by, in this case, x, y, and z, they have to be integers, right? So in this case, x would have to be 2. 2 is 100% an integer. Here, y needs to be 5. 5 is an integer. And here, z needs to be 10. 10 is an integer. If you have something like, let's say, 2 divides 5, this statement is not true. Why is that? Because when you write out 5 is equal to 2 times x, x has to be an integer. So if you rearrange for x, if you want to solve what x is, let's say you didn't know what x was here, well, you would just divide both sides by 2, and you would get 4 over 2 is equal to x, which is equal to 2, right? That's how you would get your x. Here, it would be the exact same sort of deal. To figure out whether 2 divides 5, you simply have to rearrange for x, and x has to be an integer. So in this case, we would say 5 over 2 is equal to x, which is not an integer. Why is that? Because this is a decimal. 5 over 2 is the same as saying 2.5, right? Which is not an integer. An integer has to be a whole number. So we would put a line through that line in the middle. Maybe I'll write that a little bigger. So that's what divisibility is asking. And what we're trying to say is here, what we're trying to notice when we're asking this question is, hey, in all of these examples, is it true that what's on the right-hand side is a multiple of what's on the left? So notice that when we say 2 divides 4, that is going to be the exact same as saying, does 2 divide 2 times 2? Here, when we say, does 5 divide 25, we're asking, does 5 divide 5 times 5? Here, when we're asking, does 6 divide 60, we're asking, does 6 divide 6 times 10? What do we notice about all of these? Well, notice that in all of these, what's on the right-hand side is something that we have on the left-hand side. Here, we have the left-hand side, 2, multiplied by some integer. Here we have what's on the left-hand side, 5, multiplied by some integer. And here we have what's on the left, which is 6, multiplied by some integer. So what we're trying to figure out is this always going to be true? Is it true that whatever you have on the left, in this case a, it is always going to be divisible, or a is always going to divide b if b here can be written as a times n, or what's on the left-hand side multiplied by an integer. So that is what we're actually going to be trying to prove. Now, when writing out this proof, we do need to know the definition of divisibility. And this isn't going to be a circular proof. It's a very subtle thing that I might try to explain. I'm not sure if I'll do a very good job at it, but just stare at the solution long enough and maybe you'll get why. So we need to know what the actual mathematical definition of this line is. So divisibility divisibility is defined as that for some integers, let's say x and y, where x divides y and x cannot be 0. Now let's stop for a second. Why did I add this 0? I didn't mention this 0 in any of the examples I used to explain it. Well, that's because notice that if what we have on the left-hand side here is 0, for example, if we do 0 divide 10 or 0 divide 4, like we had in those previous examples, you would then be arguing, well, 10 can be written as 0 times some integer, let's call that m, and 4 can be written as 0 times some integer, let's call this g. Now, what's the issue here? M and g must be integers. Always, always, always must be integers. But what happens if we try and find what m and g have to be? Well, we know these two numbers. Is it true that 10 can be written as 0 times something? Well, obviously not. 0 times anything is going to be 0. So this statement is never going to be true. But if we assume it's true, what are we basically saying? Well, let's find m. We're saying if we want to find m, we have to rearrange this and say 10 divided by 0 is equal to m. And here we have to say 4 divided by 0 is equal to g. What's the problem here? We're dividing by 0. You cannot do that in mathematics. That is an undefined arithmetic feature that we have. So it's actually impossible to find a g and m, which means g and m cannot be integers in this case. So that is why we're saying that the left-hand side can never be 0, whatever you have on the left-hand side of this big line, because then you're going to end up in a situation where you're dividing by 0. So that's why I have to add this qualifier that x here cannot be equal to 0. Fantastic, and we could probably leave this here, but maybe it's better to, in our definition, explain what this symbol means. So we can say where y can be written as x times k for some integer k, right? This is the definition of divisibility, and we're going to try and prove that it's true that y has to be a multiple of what's on the left-hand side. Y here must be a multiple of x, an is a multiple of a. So we're going to try and prove this. So how do we start this proof? This is a for-all proof, so we start with let. We say let an be some integers such that a divides an. Okay, what does this mean? Well, this means that then an must be a multiple of what's on the left-hand side. It doesn't matter that the right-hand side contains a. Remember, our definition just says the right-hand side, whatever it is, has to be a multiple of the left-hand side. So we can say an, the right-hand side, must be the left-hand side, a, multiplied by some integer k. So we have to say for some integer k. Now, what we can say is, well, what is n, what is k? Well, we can say that obviously you can divide both sides by a, and let's say that. So we can say dividing both sides by a, we get an is equal to ak is going to become n is equal to k. This is super important because now we can say that, okay, well, because this is equal to ak, by definition of divisibility, this 100% confirms, oh, something I forgot to mention. I keep saying, big mistake people make. You must say, and a is not equal to 0, then. Always, always, I forget to write this down, and people often always forget to write that down as well. Don't forget to write this down. Okay, back to my reasoning. So because it does in fact follow these rules, the right-hand side can be written as a multiple of a, where a is multiplied by some integer, because n is k and both of them are integers. So we can then say, by definition of divisibility, an is a multiple of A, so A does divide AN. We're going to be using this logic almost all of the time in our math proofs. We're going to always try and take something, for example, like 5 divides n squared plus n. We're going to always try and get this, whatever it's going to be, to look like 5 times something, 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 where this something has to be an integer. In this case, it's the exact same kind of reasoning. It's just the n doesn't have brackets around it, right? This is going to be the sort of logic we're going to be using, is to get everything on the right-hand side to look like a multiple of the left, to then argue that it's true that it is in fact divisible by what's on the left. So there we go. We've now proven the super fundamental proof in divisibility that it is true that for all integers a(n), A does divide a multiple of A.